So this recording is for Alex and Chanel, because they're both not here today. Boys and girls, are you guys ready? 3.2, differentiability. Okay, say it quick. Differentiability. You guys saw this word twice or 3 times already in 3.1. Anybody remember what it was at all? What is it?
Something about derivative.
Something relating to derivative. Then you are right. Something relating to the derivative. Okay. So differentiability implies continuity. Okay. Their graphs will be smooth and continuous. With a well-defined slope at each point. Some examples are, some examples, smooth and continuous curves are polynomials, you have rationals, you have trig, those are smooth, you have exponential functions, and then you have log functions.
Should we record these for Chanel?
Oh, Ryan, you're like 5 minutes late.
Or like 5 minutes more caring.
Okay.
4 or 5 minutes less. It's no.
But at least Ryan's thinking about you, Chanel. Okay. And Alex.
That's the 2 girls.
Oh. Okay. Differentiable forever.
I'm literally only thinking about David right now. Like,
Differentiable,
it is very
okay, means it has a derivative, which is called slope, at point A, comma, f of A. If f has a derivative at x equals to a, then f is continuous at x equals to a. The converse is not true. Anybody know what I mean by converse is not true? The converse is not necessarily true. Okay. Hey, what do I mean by the converse?
just because f is continuous at x equals a doesn't mean there's a derivative.
Right. So right now, if f has a derivative at a, whatever a is, then we know f is continuous at a. But the converse means if it's continuous, does it mean that it has a derivative? No, it does not mean. Okay. So the converse is not necessarily true. If I can get through all of our non-differentiable here, then we're done for the day. Okay? This is all I got to do today. These four, this whole 4 things right here. Number 1, 2, 3, 4. Just 1 page of notes. There are four different, okay, cases of non-differentiable.
The first one is going to be called a corner. Okay. Definition, here we go. You're going to have a corner where one-sided derivatives are different. That means they exist, they are just different. Okay? So the left side and the right side, they exist, but they are different. This will give you a corner. So let me give you a function that you guys all know. F of x equals an absolute value of x. In algebra 1, how do we graph this out? What shape was that? A V. You're right. Here we go. V shape it is. The problematic location is 1x equals to what? Yeah, so okay. Even just looking at it, let me make it better. Even just looking at it, coming towards 0 from the left-hand side. What's the slope? Negative 1. Coming towards 0 from the right. What's the slope? Positive 1. Can you agree that they exist, but they are different? Therefore, at 0, we call it a corner. Now, how do we prove it? We're going to use the left and right hand limits. Okay, so we're going to start with left hand derivative. By definition, the left hand derivative is limits as h approaches 0 from the left. As the formula says, limits, oops, I wrote limit twice, over f of what? What's the formula? Just a formula. A plus h or b plus h, whatever variable you use. A plus h minus f of a all over h. What's your a value in this question? 0. What's f of 0? Is 0. Okay, f of 0, 0. Well, since a is 0, f of a plus h is the same thing as f of what? F of h. So that's like f of h minus 0, right? Because f of 0 is 0. What's f of h? What's f of h? What is it? Absolute value of h. You are right. Absolute value of h. All over h. How do I simplify this? It is a piecewise. How do I know which piece to pick?
Pick the negative piece.
I get the negative piece. So would you agree that I have to pick a negative h? Okay. So if I pick negative h over h, negative h over h, what will give me a slope of negative 1? Does it match up with what we already know? That's true. Same thing with proving right-hand derivative. I'm going to jump all the way. The work gets the same. I'm going to jump all the way to here. Would you guys agree? Okay. So right-hand derivative, I'm only changing is h approaches what? 0 from the right. But when I get to here, absolute value of h over h, which piece are we using? The positive side. So technically, it's h over h, which is 1. Therefore, what do we call the location at 0? No. A corner. Okay? So there is a corner at x equal to 0. So it's not differentiable at 0. So does it have a slope at 0? No. So there are 4 cases that the derivative does not exist, and that means it's not differentiable. That's case number 1. I'm going to hold on tight. Yes?
What's the difference between a corner and a jump?
A corner and a jump? A corner meaning that it exists there.
Oh, so like this doesn't necessarily have to
it's continuous, right? I have a value, algebraic value. I even have a limit value. I just have a slope that's different coming from the right and the left. Now a jump is discontinuous altogether, okay, which we're going to use it soon. Right, next. Case number 2, where it is not going to be differentiable, is called a cusp.
C-U-S-P. Where the slopes of the secant lines approach infinity from one side and negative infinity from the other side. So when you guys are doing your right-hand derivative and left-hand derivative, if the first one's infinity, then the other one will be negative infinity, and vice versa. So an IE would be f of x equals to x to the power of 2 divided by 3. By the way, if I were to write a radical for this, how would you write this in radical form? Third root of x squared. Okay. Let's sketch it out. We haven't really seen this much in Algebra 1 or even Algebra 2. If I were to sketch this out, when x is 0, what's y? 0. When x is 1, what's y? 1. When x is negative 1, also 1. So does it look like a v? Is the increase constant like a v? No, it's the increases, right? When x is like 8, 9, 10, does it shoot up straight like a v? No, it's a little bit of what? Curve, like that, okay, like that. Remember, radical shape doesn't look like an eyebrow shape? Same thing with this. Okay. Now let's prove it. Right now, honestly, I can't tell whether the the derivative at 0 is infinity or not. Would you guys agree with that piece? Okay, it's unsure. So let's use calculus to prove. Let's do left-hand side first. The limit as h approaches 0 from the left. The formula is f of a plus h minus f of a all over h. What's your a value for this question? A is 0. What's f of a? F of 0. It's also 0. Okay. So based on that, this is going to be the limit as h approaches 0 from the left. A is 0, so it's just the same thing as f of h. True or false? Minus 0, so that's just going to be 0, over h. What is f of h? What is f of h? H to the 2 divided by 3. True or false? Divided by h. Okay. If you are dividing, the bases are the same. What do you do with the exponents? You subtract. What exponent is in the bottom? 1. But because I have to find a common denominator, can I write that into a 3 over 3?
Yeah.
So when I subtract, what am I left with? H to the, would you agree that like that? Like that. Okay. As h approaches 0 though. Okay, so now be mindful that this is h approaching 0 from the left. So what happens when you have h approaches 0 from the left? Would you agree that's the same thing as like third root of h, like that? Okay. Pick some close number, like negative what? Negative 0.0001. Third root of that. Is it still negative or positive? It's still negative. Small number. 1 divided by a small negative number is a big negative number, isn't it? So would you agree that this is negative infinity? Okay. So this right here is negative infinity. Based on my definition, the right-hand derivative should be what? Positive infinity. Let's see if it's true. I'm going to skip all the way to here. Yes or no? Yeah. So straight up, it's going to say limit as h approaches positive infinity, and then it's 1 over third root of h. What happens when you pick a positive 0.000000 and then third root that? Small too. 1 divided by a small that. It is infinity. So based on this definition, there exists a what? At a where? There is a cusp at 0. That means the derivative doesn't exist at x equals to 0. Does it exist? No. Is it continuous? Yes, but the derivative doesn't exist. If I'm going too fast, I'm going to slow down. Next one is called a vertical tangent. What's a tangent again? The line that touches a curve at 1 point. Vertical means up and down. Is that the same thing as vertical asymptote? No. Okay. Case number 3. Vertical tangent. Okay. Not the same as VA, right guys? Not the same as vertical asymptote. Okay. So when would you get it? By definition. Ready? Since I'm like invading this spot, okay. You're going to have vertical tangents. Okay. The slope actually the slopes both right and left, the slopes over the secant lines approach either positive infinity or negative infinity from both sides. Okay, this seems like it's a similar definition of the cusp, but it isn't. What do I mean by this definition? So if we were to use the derivative, left and right hand must both be what? The same, either negative infinity or either positive infinity. They cannot be swapped, okay? So I will give you an example that you already know from Algebra 1. Y equals x to the 1/3, which is the same thing as third root of x. What curve is that, by the way? How do we graph that out? Yeah, a little flat, right? Yeah, looks like this. Yes or no? Yeah, right? Like that. Again, obviously our location is when x equals to 0. By the way, what's f of 0? 0. Okay, let's prove it. What happens? I'm going to do left hand first. Left hand derivative. Limits, I'm not going to write the formula anymore, so I'm going to plug in x right away. Would that be okay with all of us? Okay, f of a plus h. What's a? 0. That means what's left? H, so f of h. Minus f of a, which is f of 0. What's f of 0? 0. So that's like actually gone. Yes or no? So I'm going to get rid of that 0. All over h. What's f of h? H to the 1/3, beautiful. So this is h to the 1/3 divided by h. The bases are the same. Subtract the power. What's left? 1 over h to the power of 2 divided by 3. If you like radicals, of course you can write it as radical. Okay. As h approaches 0 from the left, like negative 0.0001, what happens when I square it?
it's always what? Positive. And then third root of that tiny number. It's still positive. 1 divided by small, tiny, positive number.
It is really big. Let's call it what? Infinity. So this is infinity. So left hand is infinity. Right hand, I'm going to jump all the way to this work right here. Is that okay with you guys? So right hand, similarly, we're going to say, okay, well, I'm going to change h to the positive here, 0. Similarly, we say, okay, 1 over third root of h squared. H is now positive 0.001, square that, still small. Third root of that, still small. 1 divided by that small number, it's also infinity. So based on our definition, there is a vertical tangent at x equals 0, okay? Vertical tangent at x equals 0. And then last one, it's the most obvious one, which Trey already mentioned it earlier. It's called a discontinuity. Because based on the definition of differentiability, the first word in that implies what? Differentiability implies continuity. So it's not differentiable if it's discontinuous, right? Discontinuity. I have to say all these fancy words very slow. Okay, so discontinuity, by definition, discontinuity will cause one or both sides derivatives to be non-existent. So one of it doesn't have to exist, or both of them do not need to exist. Okay? So let me give you what Trey said earlier about a jump, because he's like, well, what about a jump? Here's a jump. Okay. Let's go, here's a 1. Go that way, here's a -1. That's a jump, right? Just to be lazy, let's give it a function. How about that? Y is, let's see, on the left-hand side of 0, so when x is less than 0, looks like output is always -1. True or false? On the right side, which is including the dot, greater than or equal to 0, what's happening on the right side of 0 is always what? 1. So as you can see, the slope on the left of 0 is always -1. I'm sorry, no, the slope isn't -1. The y value is always -1, but the slope is always 0, okay? Not including 0 point, obviously. So the y value is always -1. Y value. Y value is always 1, right? But the slope coming towards the center is 0 for both. Except what? At 0. So based on our definition, one of it has to be non-existent, or both of them has to be non-existent. Let's see which one's non-existent, or both. Do you think both of them are non-existent? Yeah? Okay, well, let's check. Here's the left. I'm going to straight plug in the formula. Is that okay with all of us? Limit as h approaches 0 from the left. F of a plus h, a is 0, so can I just write f of h? Now I have to be very cautious with this. What is f of 0? 1, so I have to be very mindful of that, okay? -1, is that okay? All over h. So what is f of h? Which piece should I plug that into from the left-hand side? The negative. So would I write -1 minus 1 all over h? Would that be okay? Which is really -2 over h. H is its negative infinity. I'm sorry. H is -0.0001. Negative 2 divided by negative 0.0000001, which is what? Yeah, this is positive infinity. This means it does not what? Exist. Okay. On the right side, though, does it exist? How do you know? Okay. So limit as h approaches 0 from the right. Which piece are we using for the right? Yeah, I would have to use 1 minus 1 over h. 1 minus 1 is 0. 0 divided by h is 0, which is consistent with the curve, isn't it? Coming from the right, okay. If I have, where's my graph? If I have an endpoint, wouldn't the derivative exist at all the way there? Yes or no? Yeah, so that's why it's fun. All right, that's our egg roll.